Okay, adding another tweak to our volumes of revolution. Everything we've done so far, we've been rotating around either the x or the y-axis. But sometimes you rotate around other lines, so we're going to look at rotations when we're rotating around something other than an axis. So a few examples. Now let's look at this one, the volume of the solid. When you take this region, so I have y equals x squared, x equals 0 in green, and y equals 4 in, or whatever, that's red, y equals 4 in green. And we're rotating this around the line y equals 4. So this is now my axis of rotation, the y equals 4. So we're rotating right here. Okay, this is my region that we're looking at, this little region right here. And we're wanting to rotate this around y equals 4, which is going to flip this up here. So now we're going to have a region up here, and it changes how you measure your radius. So let me take a second to get that reflected. Oh, geez. There we go. Let me take a second to get this region flipped up so we can kind of visualize what's happening. There we go. And we're going to have a region that looks something like this when we flip it up. When I take a cross section, you always do your cross sections perpendicular to whatever the axis of rotation is. So I'm cutting this this way. So there's my cross section. And you always want to identify the shape of your cross section. Now this cross section does not have a hole in the middle, so this is a disc. Or is that a C? I don't know. I always struggle with this every day. All right, so this is going to be a disc. I'm rotating around a horizontal axis of rotation. That looks a lot like my x-axis. And my cross-section, if I were to extend it, it would hit my x-axis. That makes this a dx problem, which is nice because my equation, what happened to my x squared here? There we go. My equation is in terms of x already. So now we have to find the radius. I know that the area of a disk is pi r squared, and my radius has to be in terms of x. Now when you draw your radius, you always draw it from the center, obviously starting from the center, but you always go back to the original graph. Do not draw it up to the reflected graph. That's just there kind of as a visualization. You always draw it back to your original graph. So my radius is right here. Now to find the length of that radius, there are a couple of different ways you could do it. I think of it as I'm going from top to bottom. My radius is going to be whatever the length is. It's top minus bottom, just like when we were doing the area under a curve. If we were doing top and bottom, it was the top curve minus the bottom curve. So my radius here is going to be my top point is on the line y equals 4 minus the bottom point on the line y equals, or the curve y equals x squared. So there's my radius. You always do your radius as either a top minus bottom, or if it's a dy problem, it'll be a right minus left. So we did the top point minus the bottom point. So once you get your radius in terms of x, then we'll take all of this stuff and now we plug it into the antiderivative. This will be the antiderivative of pi r squared, which would be 4 minus x squared squared. This is a dx. And now we have to decide where my x's begin and where my x's end. Now I am sliding my cross sections. When we accumulate this volume, I'm starting with my first cross section right here. And then I'm going to slide my cross sections, I'm going to slide my cross sections to the right. And I'm going to keep sliding my cross sections to the right until I get to the very last spot on my curve, which is this little bitty spot over here. So we're sliding from left to right. That's why it's a change in x. That's why it's a dx problem, because left to right is changing your x's. My very first cross section starts here at x equals 0. My very last cross section ends at this x coordinate. So we have to know where x squared hits y equals 4. So that intersection is going to be when x squared equals 4, and that happens at x equals 2. So we're going to go from 0 to 2, and that's the integral that would find the volume of this region. I'm going to come back and solve these later, but right now I just want to set up the integral. I will go through the very first step of integrating. When you have these types of problems where your axis of rotation is not the x or the y-axis, you very often have to FOIL out your radius, and that's what we have to do here. We have to expand that out completely. 16 minus 8x squared plus x to the fourth, and we just have a nice power rule. We would integrate and then evaluate from that point. Let's take another example. Here we have uh, the square root of x, x equals 9, and y equals 0. So we're looking at this region, and we're rotating it around the line x equals 10. Now this is x equals 9 right here. X equals 10 is going to be about here, and that's going to be a vertical axis of rotation. So let me drop in my axis of rotation. Let me make that black. Let's make that black. There we go. So there's my axis of rotation. So when I rotate my region around this vertical line, it's going to look something like this. There we go. So we flip it left and right, and it moves our graph over here. Whoops, I want to do that there. It reflects the graph over there. Now my cross sections, you always do cross sections perpendicular to the axis of rotation. So now I'm going to cut this one left and right, and this one is going to have a hole in the middle. This is going to be a washer cross section. I want to move that over. There. So my cross section is going to look like this. I'm going to have a big outer circle like that, going from the blue curve to blue curve, but on the inside I'm going to have a little hole, making this a washer problem. So this is a washer. If I were to extend the cross section, it would hit my y-axis. So this is a dy problem. The area of a washer is pi big R squared minus little r squared. And we have to get our big R and our little r to plug in. Now this is a dy problem. That means I have to have my equations in terms of y. So y equals x squared is okay, but that's in terms of x. I have to solve that. I'm going to square both sides and say that if y is equal to the square root of x, that means x is equal to y squared, and we have to use that formula for the radius. Now my big radius, as I said, you always do your radius from the center to the original graph. So I'm going to go from the center out to the original graph, which was over here. And now I'm going from right to left. I'm going from right to left. That makes this a right minus left radius. The right point is on the line x equals 10. So my big radius is going to be 10, that's the right point, minus my left point, which is on the curve, x equals y squared. So my big radius is 10 minus y squared. My little radius is nice because it always goes from the line x equals 10 to the line x equals 9. So if I did right minus left, that would be 10 minus 9. Or you could simply say that my little radius is always 1. Doesn't matter where I look, the distance between those two lines is always 1. So I'm just going to say my little radius is 1. And then once you have all of that information, we will plug it into an antiderivative. So this stuff becomes pi antiderivative of big R, which is 10 minus y squared all squared, minus my little r, which is 1 squared. It's a dy problem. And then my limits of integration have to be in terms of y. Jeez. Yeah, there. All right, my very first cross section is going to be way down here. I'm going to start with the cross section way down here on the x-axis, and that starts at a y coordinate of 0. And my very last cross section is going to be way up here. I need to find this y coordinate, so I'll know where my cross sections end. If x is equal to 9, this is the line y equals square root of x. My y has to be 3. So here is the antiderivative that will find this volume. Again, I'm going to clean this up to get it ready to integrate, although I'm not going to do that just yet. I'll come back and do it in a little bit. This will be the integral from 0 to 3. We do need to expand that. 10 squared is 100. Do the outers and the inners. You get minus 20 y squared plus y to the fourth minus 1 squared, which is 1. And then I will go that one last step, the ever difficult task of 100 minus 1 is 99. So 99 minus 20y squared plus y to the fourth dy. And that integral will find your volume of this solid. So remember, with your radii, you want to do top minus bottom or right minus left. Let's try this one. A little bit different. Now we don't have any lines in here. This is our region, x squared, 6 minus x squared. When graphing 6 minus x squared, the best way to get an accurate graph is to find the roots. So I'm going to find the roots of that, which you'll factor out a 6x. No, you won't. You'll just factor out an x, which will give you 6 minus x, set that equal to 0, and you get x-intercepts of 0 and 6. And I know it's a parabola, it opens down. So that's how I was able to get the graph of that red one. If you don't know what y equals x squared looks like, we're in trouble. Let's see, we're rotating this around the line y equals 9. Now this one is a little bit interesting because I need to know where y equals 9 is. So what I'm actually going to do first is find this point of intersection. So let's find that point of intersection. We'll set the curves equal to each other. So x squared equals 6x minus x squared. I'm going to move everything over to one side. 2x squared minus 6x equals 0. Factor out of 2x. 6 minus 3 equals 0. And you get intersections at 0 and 3. We already knew they intersected at 0, but we now know that these things also intersect at 3. And if y is equal to, or if x is equal to 3, this is the graph y equals x squared. So that's the ordered pair, 3, 9. So these intersect at 3, 9. And 9 actually is the axis of rotation. So I know that I can draw my axis of rotation in like this. So there is what I'm rotating this around. There's my axis of rotation, which means this little football looking shape right here is going to flip up and it's going to rotate around like this. So let me get that in real quick. There we go. Looks something like that. Now my cross sections are going to be vertical. You always cross section perpendicular to the axis of rotation. So my cross sections are going to come down like this. I'll have a big outer cross section and then a smaller inner cross section, making this another washer. We do have a hole in the middle. So this is a washer problem. It is a dx because my cross sections would hit the x-axis. I know the area of a washer is pi big R squared minus little r squared. And we have to get my big R and my little r in terms of x because it is a dx problem. Big R from center to the original outer curve. That is a top and bottom. I'm going from the line y equals 9. From the line y equals 9 to the parabola y equals x squared. So 9 minus x squared. My little radius is going to go from here to here. My top curve again is y equals 9, and we have to be careful with this one. It's y equals 9 minus, and this line is 6, or this curve is 6x minus x squared. So make sure you put that in parentheses. So minus 6x minus x squared. Ooh, this one's going to be rough. Which turns my little radius into 9 minus 6x plus x squared. And then we will take all of that and plug it into an antiderivative. Will be the integral. I'm going to go ahead and pull the pi out. Big R is 9 minus x squared, all squared, minus my little r, which is ugly, 9 minus 6x plus x squared, all squared. This is a dx problem. And it's dx, my cross sections are going to begin over here on the left at x equals 0, and then I'm going to slide my cross sections to the right until I get to x equals 3. And there's the antiderivative that would solve this. This is going to take a lot of algebra because we actually will need to expand and FOIL this out. Again, I'll come back and do that later. I'm not going to take up your time doing algebra and simple calculus, which this would just be a power rule once you get down to the antiderivative. I have one more example that I wanted to do. It is y equals 3 root x, which is in blue, 3 halves x, which is this line in green, and we're rotating around the line x equals -1, which I already have graphed in here, so we're rotating it this way. Let me go ahead and sketch this in. If we rotate that around the line x equals 1, it's going to end up looking like this. Ends up looking like that there. So we flip it over. The line x equals -1, that's my center of this region. Cross sections are perpendicular to your axis of rotation, so my cross sections are going to look like this. I'm going to have an outer circle, and then the blue graph does create an inner circle. This is another washer. So there's my inner circle. And then your radii, again, you always draw your radii back to the original graph. Let me see, this is a washer. We are cutting perpendicular to the y-axis. That makes it a dy problem. I know the area of a washer is pi big R squared minus little r squared. And now my radii, big R and little r. Big R is going to go from the center to that green line. and always go to the original curve. So there's my big radius. There's my big radius. And big radius is from center to here, but we do right minus left. My right point is on the line. Oh, this is a dy problem. Ooh, I almost caught myself. I was going to say 3 halves x, but 3 halves x won't work for the right point because this is a dy. I've got to take my equations, and I need to solve both of these equations for x to get them in terms of y. If y is equal to 3 halves x, I would multiply both sides by 2/3, and x equals 2/3 y. So now the right point, we have to use this because it's a dy problem. My right point is on the line y equals 2/3, 2 2's. That's stupid. 2/3 y. And my left point is on the line x equals -1. So minus -1, or if you're really smart, you could call that 2/3 y plus 1. My little radius goes to the blue graph of 3 root x, but again, just like that last one, I'm not allowed to use 3 root x because this is a dy problem. I have to solve this for x. So I'll divide both sides by 3 and then square, and you get x equals to y squared over 9. And we have to use that because it is a dy problem. We're going to go from right point to left point. Right point is y squared over 9. Left point is the line x equals -1, which is y squared over 9 plus 1. And then we will take that and throw it into our antiderivative. So the volume is going to be pi antiderivative. Man, my integral signs are rough today. It's embarrassing. There, I guess that's better. Big R squared would be 2/3 y plus 1 all squared minus little r squared, which is y squared over 9 plus 1 all squared. This is a dy problem. And my cross sections, it's a dy, so I know that my first cross section is going to start way down here at y equals 0, and I'm going to stack my cross sections until I get way up here at the intersection of these two graphs. So I need to find that intersection, and it needs to be in terms of y. So that intersection in terms of y, I would say, okay, 2/3 y needs to equal y squared over 9, and we'll solve that equation. So let me pause this while I solve the equation. There we go. So I get intersections of 0 and 6. We already knew 0, but now we also know the other y coordinate is 6. And there's the antiderivative that would find this volume. If you want to see the actual answers, I'll work this out, and the answers will be posted in the video notes. But these are the setups. We would have to FOIL this out. It's going to be kind of rough. The algebra is going to be a little bit tricky. But once you get done with the algebra, the integration is going to be simple power rule stuff. So there you go.